Everyone. Thanks for joining the fourth annual International Day of Women in Statistics and Data Science conference. This year's theme is Thriving in Your Environment. Just a note, we are recording the event and videos will be available on the Caucus for Women in Statistics YouTube channel. And we kindly ask that if you have any questions for the speakers, save them for the end and put them in the Q&A chat. And without further ado, I'm delighted to host this session 216, on innovative statistical approaches to mitigate data challenges in women's and maternal health. And our first speaker will be Sadie Mirzahi. So whenever you're ready, Sadie, I'll just stop sharing my screen now and you can go ahead.
Hi, everyone. Can you please confirm if you see my screen?
Yes, we can.
Okay. Thank you very much, Hannah, for the nice introduction, and Sarah for organizing this session. I am Sadie Mirzai. I'm an associate member in the Department of Biostatistics at St. Jude Children's Research Hospital, and going to talk about association analysis of imperfectly recalled health condition among childhood cancer survivors. Here is the outline of my talk. First, I talk about why survivorship research matters. Then I talk about the statistics. And finally, I conclude with some research opportunities. The reason survivorship research matters is they are a growing population. Now we have more than 85% of pediatric cancer who are surviving above 5 years. This improvement in survival rate brings a large population, which is called childhood cancer survivors, but they are in high excess of death when they age. And the reason is because they are facing several late effects as they grow. Here, this plot shows that if I compare with the control group, you can see the survivors have a higher rate of having several cumulative burden. And by the age of 50, on average, they are facing 5 serious chronic health conditions. So definitely we need to take care of this new population which are facing a high cumulative burden. We are lucky because we have two huge survivorship cohorts. Both are NCI funded. One is childhood cancer survivorship cohort, which is a multi-institutional cohort all over the North America. More than 25,000 participants are there. They started the cohort since 1994, and they have several follow-ups after that. They include sibling into this cohort as a control group. However, all the information collected here is based on self-reported survey. On the other hand, we have St. Jude Lifetime cohort, which is clinically assessed cohort. These are the survivors, the patients who are treated at St. Jude, and then they are coming back after they are surviving for 5 years. And they are coming repeatedly for screening from head to toe. They get the screen to assess their health condition. We have more than 2,400 of St. Jude Life participants who are the participants of CCSS, which gives us the opportunity to validate our analysis when we are analyzing the self-reported CCSS outcome. However, there are some issues, and that gives me opportunity to do some statistical method. The CCSS is large cohort. However, it is self-reported. One of the questionnaire I brought it here, they are asked, survivors are asked, have you ever been told by a doctor that you have or have had a series of chronic health condition? And the answer is no, yes, not sure. But if the answer is yes, they are asked about the onset age. Here we have two types of problem. One in recalling the occurrence of a specific event, and the second in recalling the onset age. And both of these problems are sources of recall bias. As you know, recall bias is a common problem in self-reported surveys, which reduces the accuracy of estimates. And even when we have a large sample size for increasing the precision, still we are facing bias. As I said, one of them is when the event occurrence is not recalled perfectly. What I mean by that is the event might happen, but the person cannot recall, which is bringing some false negative answer, or the event hasn't happened, but the person think it had happened, and it is bringing some false positive answer. We had that validated sample, we brought that, and we could do the inference for improving the association analysis in self-reported outcome. This paper is published last year, and I am not going to discuss that any further. However, what I want to discuss is when the onset age is not recalled, which we are facing some missing onset age in self-reported health outcome. Here I have another example, which is about the deficiency of growth hormone. The survivors are asked if they had this event. Some of them, they said no. Some, they said yes and provided the onset age. But some, they responded yes, but they missed to report the onset age. And that is causing this recall-based data is bringing some imprecision. Here I have, for this example, I have some proportion who didn't have the event, but among those who had the event, a higher proportion missed to report the onset age. It means the data is interval censored, but the censoring is not independent. So it is giving me chance to develop a method for informative interval censored data. What I did, I splitted the data in 3 categories: those who didn't have the event, those who had the event and could remember the onset age, or those who couldn't remember the onset age. I have some notation, which is a common notation in survival analysis, like modeling time to event or survey time, or an indicator which is indicating event happened before the survey time. But I define another indicator which says whether the person could remember the onset age or not. And I model that indicator to be conditioned, the probability to be conditioned on time of the event, survey time, and some covariates. For this survivorship research, I consider the function to be the function of elapsed time and some treatment covariates which they had. And then I'm able to have a general likelihood for those who didn't have the event, for those who had the event and remember it with some probability, and for those who had the event but forget the onset age, but we know it is sometimes before the survey time. Then we added the other covariates in the model, considering a Cox regression model to get rid of FI function and have a baseline distribution function with association with some covariates. Now, this likelihood has 3 difficulties. One is it is not observable for every individual. It doesn't have IID form. The second one is there is a semi-parametric approach, and it may bring some identifiability issue. And the third one is this integral, which is in the likelihood, and it may cause some convergence issue when I am optimizing the likelihood. So I'm going to take care of each problem one by one. The first one, it is simply I define one random variable v, which is the exact time of event, if recalled, or 0, by defining this v, and then I consider some observable random variable yi, which I could show this yi has a density with respect to some measure. And if I show the density, you can see this density The likelihood which I had is proportion to this density. Now, since I have the density, I can show some regularity condition, and then I have the asymptotic result for this estimator. The second problem was identifiability issue. However, I could show if I put some small assumption on pi function, then I can show this likelihood is identifiable for all the unknown parameters. And the third problem was this integral, which I defined pi to be a piecewise constant function, and then I got rid of that integral. Now, I showed a few more results, which helps me to simplify the likelihood as simple as this. That large likelihood now is simplifying to this likelihood, and optimizing that likelihood is exactly same as optimizing this likelihood with respect to probability masses allocated to exact recall points. And then I could show that the MLE which I am having from this likelihood exists and asymptotically unique, and it is consistent. Now, when I have all the good properties for my estimator, I can perform some simulation. This simulation setup is a little bit busy. I don't want you to go through everything, but what I want to say it is mimicking the real data. And then we run the simulation for different sample size. And finally, we compare the current status MLE, which is an unbiased estimate, but doesn't consider any time, non-informative censoring, and the proposed one. And as you can see, the proposed one is an unbiased estimator and performing better with respect to that non-informative one. Then after that, I just applied this method on that real data for growth hormone deficiency when we said we have a higher proportion of those who had the event, they missed to report their onset age. I compare the Cox regression model when we are really assuming those who don't have onset age to be removed from the population, non-informative censoring, and proposed method. And here is the results. If I want to check the association of brain radiation on growth hormone deficiency, you can see if I use only Cox model or non-informative interval censoring, I'm not able to show the significant risk factor. Moreover, if I consider a higher dose of brain radiation and use only Cox regression model, you can see it is underestimating the risk factor for growth hormone deficiency. Therefore, it seems the model is performing good. I just want to conclude with these remarks that I discussed the incomplete recall information censoring mechanism, which is informative in our case. We use some semi-parametric maximum likelihood, and we use the Cox regression model. Then I just give a quick information about some research opportunities we have in St. Jude Cloud. We have a lot of phenotype and genotype data, which is freely available to everyone. Here I provided the QR code and the link in case you want to just go and see all the visualization tool which we have in this cloud for pediatric cancer, cancer survivorship, and other diseases. And you may find some interesting data for your research. And finally, I would like to thank the participant of the CCSS, our chair department, and the Department of Epidemiology, my collaborator, Dr. Yasui, and my team members, taxpayer for funding us, NCI for funding us, and donors to St. Jude. And finally, thank you, everyone.
Great, thank you for that great presentation, Sadie. So our next speaker is going to be Ana Ortega Villa. So whenever you're ready, Ana, you can get started.
Great. Thank you so much. And thank you all for attending today. My talk will be on estimating gestational age from longitudinal measures. And this was work that I performed while I was at the NIH. And I'll just take a second to shout out folks from the NIH and my former federal colleagues and other colleagues that cannot participate in events like this today because of the government shutdown and because they are furloughed. So I'll begin with sharing my slides. So if you are someone who would like a copy of the slides or to follow along on your device, you can scan the QR code here or go onto this website and you can have access to the slides. All right, so I'll start by mentioning that the goal of this work is to expand access to information about gestational age at birth in low resource settings. And to fulfill this goal, we develop a predictor of gestational age that uses routinely collected, low cost, easy to measure maternal measurements. But why is it important to learn about gestational age? Gestational age is critical for infant care for many reasons. I'm just showing here a few. So it guides the timing for interventions that will help balance the risk of neonatal morbidity and mortality. And also it helps us understand whether an infant is delivered preterm, which is defined as under 37 weeks of gestation, or not preterm. And preterm birth is linked to higher risk of short and long-term morbidity. So if an infant is determined to be born preterm, then there are certain interventions and certain care considerations that start taking place. So understanding the gestational age of an infant is very important. And accessibility to this information is crucial. So right now, ultrasound is the gold standard for estimating gestational age, but not everyone has access to this. There may be barriers in availability in under-resourced settings. And also when there's the availability of the machine, then there's barriers associated with cost, with training, and maintenance issues. And there are some alternatives like the last menstrual period, which is something that a person has to recall. And so you recall the first day of your last menstrual period, and then a certain number of days are added. And also you can look at cross-sectional or one-time measurements of fundal height, which is the distance between the pubic bone and the top of the fundus. But we have that the last menstrual period might be subject to measurement error, maybe fundal height is not always assessed, and these measures are not always accurate on their own. And so what are things that we can collect to help us answer this question? And so during pregnancy, you can look at longitudinal measures like fundal height. So instead of looking at it cross-sectionally, you can see its evolution across pregnancy. You can also look at different skin folds. So a skin fold is basically an area that you can pinch. And so for example, if I pinch here, oh, well, you can't see, I pinch here, that's going to be my tricep skin fold. What you see here is the subscapular skin fold, and several of these are measured during pregnancy. And you can also look at weight across pregnancy. In a cross-sectional way, you can also look at the last menstrual period. So like I mentioned, you can recall the first day of your last menstrual period and then add a certain number of days to it. And so this is from the pregnant person. Now, what we can collect from the neonate at birth are metrics like length, circumference of the head, circumference of the head, circumference of the abdomen. There are other types of arm circumference, things like that. And you can also collect birth weight. And so this will be just one-time measurement when the baby's born. And so now that we have access to this information that we can collect either longitudinally or cross-sectionally from the pregnant person or the baby, how do we develop our predictor? And so in order to do this, you can think of a full data set with all the information split into two. A training set that contains 60% of the data, where we have gold standard measurements of gestational age. And with these data, we can develop our model, estimate the necessary parameters, and then assess the prediction of the predictor developed in the training set in a test set to understand how well or poorly we're presenting. And so to make things easy, we can start thinking about this two-step procedure, let's say, looking at one longitudinal measure. And so you can think of fundal height as one longitudinal measure that you measure across pregnancy repeatedly. And so you can think of YIJ as that measured fundal height for each participant I at each visit J. And then you can split the gestational age at the visit into two. The gestational age at the first visit plus the time between the first visit and visit J. And so if you take the gestational age at the first visit plus time in between the first and subsequent visits, you're going to have gestational age at each of the visits. But splitting it into these two components will help us then later understand what's going on with gestational age and be able to take it out of here and predict it in the test set. Now, this is the standard layered and weighted formulation. And we have some assumptions here about our random effects, about the distribution of gestational age at first visit. And we do our estimation via maximum likelihood. Once we have estimated the parameters of interest, which are our overall coefficients beta 0 and beta 1, information about our random effects, so that variance of the random effects, that variance of the error term, the mean and standard deviation of gestational age at first visit, we can use this information to then predict. And so the way we do this is we calculate the expectation of gestational age at the first visit, given information about the longitudinal measures of fundal height, the parameters from the model. And just like we did it for one longitudinal measures, we can expand this and we can simultaneously include multiple longitudinal measures. So not just fundal height, but include information about our skin folds, about weight and anything else. We can also include multiple cross-sectional measures simultaneously. So thinking about the last menstrual period information, but also about these neonatal measurements that we collect. And we can do this using a shared random parameter formulation. And after looking at our data, we found that adding additional measures on top of fundal height does not meaningfully improve our results in a way that it makes sense clinically. So looking at fundal height alone, we found that we had estimates within about 2 weeks of the truth, and adding other measures only improved this in a matter of days. So clinically, that really doesn't provide a lot more information. And because what we're looking for is access, then keeping it simple and looking at one easy to measure longitudinal metric fulfilled what we were intending to do. Here is our paper This is joint work with Catherine Grants and Paul Albert. And we also developed a calculator where folks would input their fundal height measurements in centimeters along with their visit dates. And this calculator would provide an estimate of the gestational age at delivery. Now, we have a potential issue. And it's that the population that we trained our predictor on, the one that we use to develop our calculator, may not reflect the population that needs it. So the data that were used in the creation of this predictor was from the National Institute of Child Health and Human Development fetal growth study of singleton gestation. And this is a prospective cohort study of 2,334 healthy, non-obese pregnant women in the United States population, all with access to ultrasound, which, as we know, it's the gold standard for assessing gestational age. So then it looks like it's possible that the population that we use to train our predictor may not reflect the population that needs it in an under-resourced setting where there's no access to ultrasound. But if the model could be trained on a population that resembled that target population, it may be that not all the individuals in the training set had access to ultrasound. So then what are the options that we have? I'm seeing something in the chat, sorry. Okay. So our options are that we can incorporate information about the last menstrual period for those people who do not have ultrasound assessed gestational age. But as we know, the last menstrual period is subject to recall bias. And so we need to account for this in our predictor. And so if you recall from a few slides ago, this is the model that we were using when everybody had access to ultrasound. And we estimated this model using maximum likelihood. But then what happens if not everybody in that training set that we're using has ultrasound? So it may be that some people in the training set will have ultrasound, determine gestational age at first visit. And then some people in the training set will have the last menstrual period and not the ultrasound determined gestational age. Then we can look at the relationship between the last menstrual period and the ultrasound determined gestational age if we have this restriction that if they have ultrasound determined gestational age at first visit, they must also have last menstrual period information. And then we can use this relationship and account for it in the likelihood function. So for example, we can assume that the last menstrual period is normally distributed with mean gestational age at first visit and some variance. And so now that we account for this, in the likelihood, we have then two options for our predictors. Option one, looking at a training set that only looked at ultrasound gestational age, will be exactly like before. The expectation of gestational age given fundal height, all my parameters, looking at parameters from the model that only considers those folks who had ultrasound assessed gestational age at the first visit. But if now we want to also incorporate last menstrual period information, we then go to the likelihood that we maximize that account for this information, and we estimate and we develop our predictor again, looking at that conditional expectation of GAI or conditional expectation of gestational age at the first visit, given my fundal height and then the parameters from the model that considers ultrasound assessed gestational age at first visit and recalled last menstrual period. So it's note that we have this variance estimate here. And so then we want to look at how our predictor performs. And so, we can look at the NICHD fetal growth study, which is the only data that we had. But we encountered an issue, and it's that GAI and LI by design were in a narrow range so that they ensured accurate gestational age assessment, because they were developing this fetal growth study of singleton gestations for developing growth standards. And so they needed the gestational age to be really accurate. So instead of using that observed, we simulated the last menstrual period with measurement error from this normal distribution with mean GAI and variance sigma squared 2. We found that even in a case where we only had 5% of folks with the simulated last menstrual period, we saw some gains in the accuracy of the estimation, noting how things get closer to that 45-degree line. So this is just an amuse-bouche of everything that we did in our paper, which you can find here. And so if you have any questions or any thoughts, you can reach me in my contact information from the website. I will put it on in the chat. Thank you.
Great, thank you, Anna. So our next presenter and the final presenter for this session is going to be Kimberly Hochstedler-Webb. So whenever you're ready, Kimberly.
Great, thank you so much. Today I'll be presenting a talk entitled The Misdiagnosed Mediator, Estimating the Effect of Maternal Age on Preterm Birth Risk in the Presence of Misclassified Gestational Hypertension. And just like Anna, if you'd like to follow along with these slides on your own device, you can use the link that's on screen or the QR code that's on screen as well. All right. So to begin this talk, I'm going to frame kind of what a mediation analysis is, since that's the main type of analysis that I'm going to be discussing. A mediation analysis in general quantifies the effect of an exposure that I'll call X on an outcome variable that I'll call Y. And importantly, this XY relationship is mediated by some intermediate variable that I'll call M. The easiest way, in my opinion, to understand this is to see this exposure, mediator, and outcome relationship in pictures. So that's what I'll show next. In our setting, our exposure variable is maternal age and our outcome variable is preterm birth. So you can imagine a kind of direct relationship between X and Y, or between maternal age and preterm birth. But we also have this additional intermediate or mediator variable called M, which is gestational hypertension. So now you can see that this XY relationship isn't just direct. X might also be associated with M, and then M in turn can be associated with Y. So we could have this indirect relationship as well. So our overall goal is to understand this relationship in our study, but we have a few complicating factors beyond the kind of traditional mediation analysis. So in our particular case with gestational hypertension, this condition is not something that's measured perfectly. So measurement of M or gestational hypertension is not always accurate. And instead of getting to observe M directly, we end up with M star, which is gestational hypertension diagnosis, and it does not always match someone's true status, right? So someone could be misdiagnosed. And in our setting, we have an additional variable, Z, that's patient insurance status. And Z in this case is related to the misclassification mechanism. And what this means is that someone's value for Z, whether they have health insurance or not, might be predictive of whether or not they were misclassified or misdiagnosed for gestational hypertension. Right. So as you might imagine, our typical mediation analysis is really complicated by this misdiagnosis in M, in our mediator variable. And I want to highlight a few reasons why this misclassification is especially difficult to deal with. So the first is that our misclassification is covariate dependent, right? So Z is related to the misclassification rate in our data set. So that makes it really hard to deal with because we have this variable that is really influential in our data set. In addition, we don't have a gold standard measure for M. So there's no perfect gestational hypertension diagnosis in our data set. Anyone could be subject to misclassification, and we only have the noisy version in our data. We only have M star. So for the remainder of this talk, I'll be viewing M, or true gestational hypertension status, as a latent variable. That means we have this construct for it. We understand that gestational hypertension is a thing, but we don't have data on it at all. It's purely a latent variable in our case. If we were to perform a typical mediation analysis in our setting, basically ignoring the potential misdiagnosis in M, we would end up with bias in our parameter estimates, and that's something we're trying to avoid. So for the rest of this talk, I'm going to describe kind of how we deal with this complicated mediation analysis structure. So first, I'm going to share the mediation model that we use in this setting. Second, I'll share the estimation methods that we developed for this project, and then finally, I'll apply those methods to the applied example that I was sharing earlier. All right, so first I'm going to use this diagram that was on the previous set of slides to walk through the model that we're applying to this situation. First, I'm going to highlight just X and M's, the exposure and the mediator variable, for our true mediator mechanism. Here we're modeling the probability of gestational hypertension, someone's true gestational hypertension status, as a function of beta parameters, the predictor of interest X, and then we also have this C term, which just stands for general covariates. And this should look a lot like a logistic regression model. We just have a latent variable in our outcome. Next, I'll bring in Z and M star for the observed mediator mechanism. So here we're modeling the probability of gestational hypertension diagnosis conditional on someone's true gestational hypertension status as a function of gamma parameters, and then that variable Z of patient insurance status. And this too should look like a logistic regression model, but we have a conditional probability inside of the logit function. And finally, I'll bring in the outcome variable of interest Y in our outcome mechanism. So here we have the expected value of Y modeled based on these theta parameters, the exposure variable X, those covariates C, and we also have a term for the true mediator M, and we allow for an interaction between X and M, so that exposure and the mediator. I want to direct your attention to the beta and theta parameters. These are the mediation parameters in our model, and so they're really the thing we're trying to estimate. This is the main goal of this study. So beta and theta really quantify this exposure, mediator, and outcome relationship that we're interested in. So these are the things we're trying to estimate. These gamma parameters, though, are also quite useful. I think of them as misclassification parameters. They essentially account for all of the misclassification, or hopefully all of the misclassification that's happening in our system, so that beta and theta can do the thing we actually want them to and model misdiagnosis, and model the mediation framework. So you can think of gammas as a little bit more of a nuisance parameter, but they tell us about misclassification. Right, so now that we have these parameters, I want to share the way that we're going to estimate them. In the paper associated with this project, we have 3 different estimation methods that we provide, and in the interest of time, I'm just going to go through the last one in a little bit more detail, but I wanted to share the overview of the first 2. So the key point of the first 2 methods that we provide is essentially that we can use an existing method that I developed called Combo to estimate subject level sensitivity and specificity values for the mediator variable. And we can then plug those values into existing misclassification correction procedures. So the OLS correction and the predictive valuating approach, they already existed. They just relied on known sensitivity and specificity. And so our innovation is estimating sensitivity and specificity at this subject level and kind of factoring that in to those estimation procedures. I'll spend a little bit more time on the EM algorithm because this is a more seamless approach to estimation, and it tended to perform better in simulation studies. So for the EM algorithm, we start out with a complete data log likelihood function. You don't need to worry too much about the details, but what I want to highlight is that this function contains components from each of those mechanisms that we just went through. So there's a component for the outcome mechanism, for the true mediator mechanism, and for the observed mediator mechanism. And importantly, all of these components contain M. They contain the true mediator. What's challenging about that is, again, M is latent. We don't actually have data on it. So there's really nothing we can plug in to this equation in place of M. And so that's where the EM algorithm comes in. Since we can't maximize this likelihood directly, we have to turn to something else. All right, so for our EM algorithm, as usual, we're iterating between an expectation and a maximization step. For the expectation step, we compute this weight term, or Wij. This is the probability that individual I in our data set has true mediator value J, conditional on everything else in our data set. And I'm just going to ask you to trust me on the exact form of this probability. But the key point is that this probability is essentially like our best guess for our mediator variable in the presence of everything else we've got. So current parameter values and all of the other data in our data set. Then given that best guess, we take the complete data log likelihood function from the previous screen, and everywhere there was an M or a latent variable, we plug in our best guess for that latent variable from the E step. Now we no longer have a missing, value essentially in our likelihood function. We can maximize it like usual, get our parameter estimates, and iterate back and forth until we reach convergence. For a typical EM algorithm, once we iterate to convergence, that's when we would stop. But because we're dealing with a latent class mixture model, we have to do the extra step of applying a label switching correction, which I provided more details in a different paper. All right, so that's our general estimation method, and I want to take us back to the applied study that really started all of this. So we applied our methods to this preterm birth study where our goal was to understand if gestational hypertension mediates the association between maternal age and preterm birth. We wanted to understand this mediation relationship after accounting for potential misdiagnosis of gestational hypertension based on patient insurance status. The data that we used to answer this question was from the National Vital Statistics System, which provides demographic and health data for all births in a calendar year in the US. As you can imagine, there's a lot of data in that data set. And so to make this computationally feasible, we took a random subsample from the year 2021 of 20,000 observations. And on this slide, I'm just giving you details on kind of the exact models that we were fitting for this example. So our true mediator mechanism modeled gestational hypertension based on that key exposure of interest, maternal age, and then we also had covariates of race, education, parity, smoking, and BMI. And then for the observed mediator mechanism, we were modeling gestational hypertension diagnosis, conditional untrue gestational hypertension status as a function of patient race and insurance status. And finally, for the outcome mechanism, we were modeling the outcome preterm birth as a function of all those same variables from the true mediator mechanism. And of course, we also had a term for gestational hypertension and an interaction term between X and M. On this slide, I'm going to give you the parameter or the results for a couple key parameters from this study. So the left set of columns will have results from our EM algorithm that accounts for misdiagnosis in M, and then the right set of columns has results from a naive mediation analysis that does not account for misdiagnosis. First, you'll see results for this beta X parameter, which tells us about the association between maternal age and gestational hypertension. And if you look across the two estimation methods, this estimate is really unchanged. So we don't think that misdiagnosis is really impacting this association. But the story changes if we look at association parameters from our outcome mechanism, particularly theta M. This tells us about the association between gestational hypertension and preterm birth. And if you look between the naive approach and our approach, the association actually strengthens, which tells us that when we account for a misdiagnosis of gestational hypertension, the relationship between that condition and preterm birth appears to strengthen. So, accounting for this misdiagnosis kind of matters for this relationship. And finally, we have these gamma parameter estimates. These have interpretations of their own, but kind of the easiest way to understand the gamma estimates is to use them to compute sensitivity and specificity, which I'll do on the next slide. But before I do that, I just wanted to draw your attention to that very large standard error for the second gamma term. That will also be explained on the next slide. So here I have estimated sensitivity and specificity computed using those gamma parameters. What you might notice right away is in the specificity column, we have near perfect specificity. So what this means is regardless of your insurance status, for women that don't actually have gestational hypertension, they have virtually no chance of being diagnosed with it incorrectly. So that's actually the reason for that very large standard error in the second gamma parameter estimate. We think we're reaching some kind of ceiling effect on that parameter because that's the term that corresponds to the specificity mechanism of our system. But when we turn to the sensitivity estimates, we have really a different story here. So what these results say is that among patients who are insured, we expect, or among patients who are insured and who actually have gestational hypertension, our estimates suggest that only about 43% of them will be correctly diagnosed. And among women who do not have health insurance, this probability drops to under 22%. So we're seeing really pretty low sensitivity in our estimates and a big disparity based on insurance status. Right, so with that, I'd just like to share a couple key takeaways from this work. So first, we developed new methods for handling misclassified binary mediator variables, and we can use these methods to compute, hopefully unbiased or bias-corrected parameter estimates. And we can also quantify things like gestational hypertension misdiagnosis rates based on other factors in our data, like insurance status. And if you're interested in trying out these methods on your own data, we have a couple R packages. So all the methods that I shared today are in the R package called Comma, which is on CRAN. And then there's also an R package called Combo, which has some methods for outcome variables. And with that, I'd like to thank you all for your time today. I have the paper link on screen as well as my website and email address if there are any questions, but thank you all very much.
Okay, thank you so much, Kim. So that was our final presentation for this session.